Okay, I think I can start because this will be just an introduction. So thank you everybody to be back on qmeets. Today we are very pleased and glad to have two great speakers. One is Nicole Younger Halper, and she's a theoretical physicist at University of Maryland. Um, her works, uh, her work is basically on quantum information and thermodynamics, as the title suggests. And she studied in Perimeter Institute um, during her master degree, and then moved to Caltech for her PhD, which she did with John Preskill, if I remember correctly. And now she is based in Maryland, and she's studying quantum information and thermodynamics. And then we have José Antonio Marín Guzmán, if I pronounce it correctly. Correct me if I'm wrong. And he's a PhD student at the University of Maryland, and he studies quantum information, thermodynamics, and theoretical design and implementation proposal for autonomous quantum machines. So today they will talk about these broad topics, that is quantum information and thermodynamics. So I'll give the floor to Nicole, and please.
Great. Thanks for the introduction, and thanks for the invitation to speak in this series. Thanks to everybody else for joining. I understand that this is a relatively sophisticated crowd when it comes to quantum information, so I figured I could start with a technical term, namely steampunk. Steampunk is a genre of literature, art, and film. My favorite description is set in the late 19th century. It encompasses all of the romanticism of the Victorian era, then cranks up the technological level to 11. The steampunk stories feature settings from the 1800s, with some of the earliest factories, grimy London streets, Meiji Japan, La Belle Epoque in Paris, the American Wild Wild West, and so on. But in these 1800s settings are futuristic technologies, time machines, automata, flying ships, submarines, that sort of thing. The steampunk has this fusion of the old and the new, which creates a lovely sense of adventure and exploration and romance. The people dress up in these steampunk costumes and go to steampunk conventions. I like to say what they dream, quantum information thermodynamicists live. Let's break down that term. Thermodynamics, probably all of us here have studied, although I find that a lot of physicists don't actually know the definition of thermodynamics, especially ones who say that they specialize in something like non-equilibrium thermodynamics. But just to make sure we're all on the same page, let's review what thermodynamics is. It's the study of energy and temperature, so quantities such as heat and work. It was developed during the 1800s, in other words, during the steampunk era. It was inspired by the Industrial Revolution. For the first time, engines were powering factories which were transforming the face of civilization. So naturally, people wanted to know how efficiently these engines could operate. They developed the theory of thermodynamics from a practical perspective, but these technologically motivated questions led to answers about some fundamental physics questions, such as why does time flow in only one direction? Thermodynamics was inspired by one of the transformative technologies of the day, steam engine. So that was a large classical system. In contrast, some of the transformative technologies of our day are very, very different. For instance, experimentalists have great control over small systems. This is a sketch of a single strand of DNA. You can use optical tweezers consisting of lasers to trap one end of the DNA strand and then pull the other end of the strand. You can measure the work required to pull the strand through a given distance. Of course, a lot of us are interested in quantum systems. This is a picture of, I think, one of IBM's dilution refrigerators in which a quantum computer can be cooled down. Of course, most systems, in order to exhibit quantum phenomena, need to be at very low temperatures, so they need to be cooled. And cooling is the expulsion of heat, so it is a thermodynamic process. We can also evaluate the relationship between energy processing and information processing. Now, a lot of really interesting out of equilibrium experiments have happened recently. I mean, apart from all of us here, all living beings are far from equilibrium. But for instance, in some quantum labs, one can have, say, a bunch of ultra cold atoms and then kind of hit them so that they come far out of equilibrium, and then we can see how they come back down to equilibrium. These settings are very different from the conventional thermodynamic setting of a factory in industry. But thermodynamic concepts such as work and heat are relevant. We therefore need a new toolkit. We need to re-envision thermodynamics for these new settings. And quantum information science offers such a toolkit. By quantum information science, I mean the study of how we can use quantum phenomena to process information in ways that we can't if we have only classical systems. Uh, I mean, a number of things by process information. Solve computational problems, communicate information, secure information cryptographically, and store information in memories. I also mean a number of things by quantum phenomena. For instance, entanglement, the non-commutation of operators, the discreteness of spectra, how measurements tend to disturb quantum systems, and even more. Quantum information theory was motivated in part like thermodynamics, in part by the promise of quantum technologies such as quantum computing. But regardless of the origin of quantum information theory, it's now a wonderful mathematical and conceptual toolkit, now complemented with an incredible experimental toolkit. And this toolkit can be now applied across science. So we use quantum information science to gain new lenses onto high energy physics, black hole physics, chemistry, atomic molecular and optical physics, and thermodynamics. We can take the thermodynamics from the 1800s and update it for the 21st century using quantum information theory. The result is quantum thermodynamics. This field I see as following three guiding questions, or guiding principles, perhaps. We can take the laws of thermodynamics that were developed in large part during the 1800s. They were designed for large classical systems. We can extend them to see exactly how and why they govern even systems that entangle with each other. And sometimes from the laws of quantum mechanics, we can derive more precise, more refined versions of the thermodynamic laws. For example, engines and refrigerators, particularly engines, play a very important role in the laws of thermodynamics. These are subject to the law of conservation of energy, and one can phrase the second law of thermodynamics as Carnot's theorem, as a bound on an engine's efficiency. José Antonio is going to talk about a take on this goal of quantum thermodynamics. Second, we know from quantum information processing that quantum phenomena such as entanglement can enhance information processing tasks such as computation. Just as there are information processing tasks, there are thermodynamic tasks, such as charging batteries and extracting work and cooling systems. We can ask how quantum phenomena can enhance those thermodynamic tasks. Finally, we can look at a system that's processing energy and other thermodynamic quantities and ask, what behaviors can a system exhibit if it's quantum and not if it's classical? We can use thermodynamics to understand better the division between the classical world and the quantum world. And I see quantum thermodynamics as the real world version of steampunk because we have thermodynamics from the Victorian era, and quantum information science, which is partially cutting edge and partially futuristic. We don't have large-scale quantum computers yet. So we have that blend of old and new. So I like to call this field quantum steampunk. I'll illustrate quantum thermodynamics with a few stories that illustrate the relationship between information and work. I'm going to argue that both information and work can serve as resources in both information processing and thermodynamics. We'll start with the story of Szilard's engine. Leo Szilard was a great Hungarian-American physicist of the 21st century. Excuse me, the 20th century. And this story actually grew out of his PhD thesis, which Einstein complimented him on. So I like to hold this up as an example of something that students can aspire to. So may you too write PhD theses that are worthy of complimenting from Einstein. Szilard argued that if we have information, we can use it to transform heat into work. Heat is uncoordinated energy. It's the random particle, or the random energy of particles just jiggling around. So it's not directly useful for doing something like pushing a rock up a hill. Work is coordinated, directed, directly useful energy. We can use information to turn this kind of useless heat into useful work. Suppose that we have a classical particle in a box. This will be a very, very simple model for an ideal gas. Suppose this gas exchanges heat with its surroundings through the box's wall. The surroundings have a fixed temperature T. Suppose we start with one bit of information. We know that the particle begins in the right-hand side of the box rather than the left-hand side. We can slide a partition into the box, then tie a rope to the partition and connect the rope via pulley system to an Acme anvil. Then we can unfix the partition so that it can slide. This particle is going to punch the partition, and it's going to keep punching the partition until the partition reaches the side of the box. Now, we have lifted the anvil, so the anvil has gained gravitational potential energy. We've done useful work against gravity. Where did that energy come from? It used to be heat. It came from the heat bath. So we have converted heat into work. How much work can we perform on average under ideal conditions? This type of work is pressure volume work. So we integrate pressure with the differential volume element. We all remember the ideal gas law from high school. Pressure times volume equals the number of particles times Boltzmann's constant times the temperature. We can solve for the pressure in terms of the volume and substitute into the integral. I'm integrating from v over 2 to v because the particle begins confined to half the box, but ends up being able to be anywhere in the entire box. We integrate, we evaluate the limits, and we find that on average, ideally, the particle can perform an amount kT log 2 of work. We have performed this work on the anvil, but at a cost. We now have no idea where in the box the particle is. So we have forfeited our bit of information. We've traded information for work. We can reverse this process and perform what's called Landauer erasure. Rolf Landauer was an information scientist at IBM. He said, suppose that we have a bit that we would like to reset. So there's a particle in a box. We have no idea where the particle is, and we want to reset the particle to a well-defined, nice, clean state, say the right-hand side of the box. This is like taking a sheet of scrap paper that has been scribbled on totally randomly in some language we can't read and erasing a piece of paper to a nice, clean state. Suppose that we begin with a lifted anvil, the capacity to perform work. We can reset the particle by sliding a partition into the box near the left-hand side and pushing the partition to the box's center. the particle will end up trapped in the right-hand side. Since we're compressing a gas, we have to perform some work. And the amount of work we have to perform is at least the amount of work we could have gained from Szilard's engine. So we've forfeited work, but we've gained information by returning the bit to a known state. So this story has deep implications for the relationship between computation and thermodynamics. Suppose that we want to compute and compute and compute and compute. Eventually, we'll run out of scrap paper. The universe doesn't have an infinite supply of scrap paper, so we'll have to erase some. We're told by Landauer that erasure costs thermodynamic work. So computation has an intrinsic thermodynamic cost. When I first learned this story, I was an undergrad in my senior year of university, and I thought the story was kind of magical because we learn about energy processing and thermodynamics in the physics department, maybe engineering, maybe chemistry. But we learn about information processing in the computer science department. And until fairly recently, there was almost no overlap in terms of courses between the two subjects in one department. But it turns out that there is this really, really deep connection between thermodynamics and information processing. But I've been telling you a story about a classical gas in a box, and oh gosh darn it, this talk is called Quantum Steampunk, so where does quantum physics come in? It can come into the story in a number of ways. There are multiple quantum phenomena, as we discussed in the context of a much earlier slide. These phenomena can affect our stories of Szilard's engine and Landauer erasure in different ways. For instance, one could consider using entanglement or indistinguishable particle statistics or non-Markovianity of the bath, and so on and so forth. I am going to focus on entanglement. The results I'll sketch appeared first in this paper. Suppose that we have not a classical bit, but a qubit that we want to reset to the 0 state. This qubit may be entangled with a memory. And again, there's a heat bath around from which we can draw heat. The result is that we can erase the system, we can reset it to the 0 state, while keeping the memory's reduced state fixed, while extracting net positive work. But this result should sound surprising because, again, according to Landauer, we need to pay net positive work in order to erase a system. And this result says we can extract net positive work. The trick is to kind of burn the correlations between the system and the memory. Suppose, for simplicity, that this memory consists of one other qubit, and the system and memory are in some Bell state. That Bell state is known. It's one of the 4 Bell states often denoted like this. Just imagine that we chose to perform a Bell measurement. A Bell measurement would have one of 4 possible outcomes. We would be able to predict in advance with complete certainty which outcome we'd obtain. That means that we are currently, by knowing which state the whole system is in, we are holding 2 bits of information. We can use each of those bits via a protocol that I won't specify here in Szilard's engine to extract an amount kt log 2 of work. After running Szilard's engine twice, we extract an amount 2 times kt log 2 of work. We can use one of those units of work to erase the system of interest, and we have one of those units of work left over. In summary, if we take quantum information such as entanglement and combine it with heat, we get a kind of thermodynamic fuel. In summary, we saw that we can use information to turn kind of useless heat into useful work. Also, information, including entanglement and work, both serve as resources in computation and thermodynamics. In case you're interested in quantum thermodynamics as a whole, I can recommend some basic background references. Here are some introductions to the fields. This is a textbook. There's actually at least one earlier textbook about quantum thermodynamics. These are two reviews that originally came out in 2015. And this field is moving really quickly, so a lot has happened since then, but these provide good foundations. There's also this book that I wrote about the history of quantum thermodynamics, the background we need in order to understand the field, the many, many subfields of quantum thermodynamics, and key results therein. As I mentioned, the field is moving very quickly, but here are two snapshots in time of what's happening right now and what are the big challenges right now. One such snapshot was published as this book in 2018. This is called the Roadmap on Quantum Thermodynamics. It presents what's happening in quantum thermodynamics right now and what a number of people see as challenges for the next 5 years or so. And this is going to be published hopefully within a few weeks. A more focused snapshot on one subfield of quantum thermodynamics, José Antonio is going to talk about. This is a key issues review and reports on progress in physics about useful autonomous quantum machines, the subject of José Antonio's talk. That's all I have to share. I believe that now the field is open for questions.
Yes. Is there any question for our speaker? Okay, perhaps I'll start. So I'll give a kick to somebody that wants to join. So what other quantum resources can do the same trick as entanglement did in your example for getting work or something that is
So
interesting?
different quantum resources or resources in general can lead to different variations on the story, not
Okay.
necessarily the exact same result as being able to get out work while erasing.
Mm.
But for example, suppose that we look at particle statistics. Suppose that we use in Szilard's engine not one particle, but two particles. These particles might be distinguishable, they might be bosons, or they might be fermions.
Mhm.
We can ask, how much work can we extract from the Szilard's engine on average per trial? As it turns out, we can obtain more work on average from bosons than we can obtain from distinguishable particles, and we can obtain more work on average from distinguishable particles than from fermions. The basic intuition about why the bosons perform best is the following. We, at the beginning of our protocol, will measure where are the particles. If the particles are distinguishable, then particle A and particle B can be on the right-hand side, particle A and particle B can be on the left-hand side, or particle A can be here while B is here, or they can be reversed. When under which of these conditions can we extract net positive work from the engine? When both of the particles are on the same side. Because in that case, they exert a non-zero pressure on that partition so they can push the partition. If the particles are on opposite sides of the partition, then their pressures cancel each other out. Now, bosons, loosely speaking, like to clump together. So you will tend to find them more often on the same side of the box. And so in more trials, bosons will be able to exert a non-zero pressure on the partition. And that's why the bosons work best.
Thank you. That was illuminating. Is there any other question?
Maybe I can ask a couple of quick questions.
Yep.
First of all, thanks for the amazing talk. I really enjoyed it. The first question is on the line of what Daniele asked. When you mentioned non-classical resources, then you meant, for example, already what you just gave us as an example, or you had in mind even other resources, like what was the idea of non-classical resources?
My personal favorite example resources in the context of Szilard's engine and Landau erasure are entanglement and particle statistics, which is why I mentioned those. But lots of papers have been written about Landau erasure and Szilard's engine in the context of quantum mechanics. But Andrew Gardner, a number of years ago, wrote a review about specifically quantum. It might have been Maxwell demons, it might have been Szilard engines, it might have been Landau erasure, but he goes through a number of papers that have been written that show that different quantum phenomena can have different effects on the story. Another example is suppose that at the beginning of our protocol, we need to measure a particle to figure out where it is. Well, measurements cause measurement disturbance. And we also talked about dropping a partition into a box. A classical particle will not feel the dropping in of a partition, but a quantum particle could be in a quantum state. I mean, think about the energy eigenstates. In particular, the position basis eigenfunction of a particle in a box, the energy eigenfunctions. The energy eigenfunctions have shapes that depend on the box's length. So if we suddenly halve the length of the box, then we are drastically, suddenly changing the particle's state. And so merely putting a partition into the box could be an act of performing a lot of work. So those are a few other examples. Again, Andrew Gardner collected a few, probably the Lex and Ref books on Maxwell's Demon have more examples. There have been multiple reviews written about quantum Maxwell demons. Szilard's engine and Landau erasure feed into the story of Maxwell's demon. That's why why these stories are often grouped together. So there can very well be other examples of quantum phenomena that affect the story in other ways.
That's really interesting. Thanks. And another quick question was about what you meant, just very basic question. What you talked about classical particle in a box, you talked about the bit of information and is like related to the position information, like knowing that is on a given half. And this is what I call one bit.
Yes.
Okay, thanks.
I think we can have room for one quick question. That is thus.
I have a quick question. So it's a bit more basic. So when you showed the quantum version of the engine, I was wondering what is the effect of the width of the wall that you drop, because I guess if the width is not big enough, then the particle can like teleport through, like jump through the teleport through that barrier, and then in that case it will push from one side, then at some point it will teleport to the other side, and then it can push it on the other way. So I guess there is an effect of the width of the wall also on the work that we can extract.
That seems like it could be possible.
Okay,
and there's been at least one paper, possibly a series of papers, a number of years ago that Andy Garner reviewed in his quantum, whatever it was, Maxwell Demon or Szilard engine or Landau erasure paper that focused specifically on the wall. I don't know whether that property was mentioned in those papers. It's possible. I'm not sure if it's appeared in the literature, but I agree that it should be taken into consideration.
Okay, thanks.
So I think we can stop for the question now. We thank again the Nicole, and I think we can go ahead with the next speaker. And so please.
Yep. Let me just set up the slides. Are you seeing my?
Yes.
Are you seeing my screen right now?
Perfectly. Yeah.
Wait, let me just. Oh, sorry about that. Okay, are you seeing the screen?
Yeah.
I have some weird prompts on my side.
Yeah.
So
perfect.
Okay, so well, first of all, thank you for having me here. I'm going to be speaking a little bit more on the applied side of the subject that Nicole presented a while ago. I'm going to be talking about this particular instance of a useful autonomous quantum machine that serves to cool down or reset a superconducting qubit. So, okay, quantum thermodynamics. Nicole did a way better job that I could possibly do to convince you that quantum thermodynamics and like the insights of quantum theory in thermodynamics has been a history of theoretical triumphs. However, when it comes to actual applications, quantum thermodynamics falls a bit short. Now, it's actually fair, I would say, to expect some sort of like practicality or like technological insight from quantum thermodynamics, because classical thermodynamics, as Nicole explained before, informed a lot of the technologies in the Industrial Revolution, and being able to apply this framework to the quantum domain should, in principle, yield something. It's not an unfair expectation. So a small step towards this is to think about autonomous quantum machines. So autonomous quantum machines are quantum devices that perform useful tasks without the need of time-dependent external control. In quantum thermodynamics, we think of work inputs into the system by changes in time over time in the Hamiltonian. So an autonomous quantum machine is basically a device that, being described by a time-independent Hamiltonian, doesn't have any work input into it. Now, in order to do tasks, in order to do things, the autonomous quantum machine is going to harness a non-equilibrium free energy source. For example, it can harness the heat flow of two different heat baths at two different temperatures, siphon some of that energy, and perform some task. Of course, this is just an example. This is the relevant example that I'm going to be discussing today. But this can be, in principle, some other type of free energy source. For example, a recent experiment regarding quantum clocks used a chemical potential gradient in a voltage bias in a quantum dot to do a timekeeping task. The task that I'm going to be focusing is qubit reset in superconducting platforms. So the outline of my talk, I'll talk a little bit about qubit reset, give some context, explain the setup of our system and the experiment, give the actual results, and give some conclusions outlook. So qubit reset is a crucial task in quantum computing devices. One of the Vincenzo's criteria for a quantum computing device tells us that having a supply of fresh, clean qubits, to say so in a way, to compute is something that a quantum computer actually needs to function. And this fresh supply of qubits can be seen as simply taking qubits to their ground state. So this task of depleting the energy in qubits, it's what we're going to be focusing on. How do we quantify the success of such a reset protocol? We do this by looking at the population of the excited state of the qubit. Now, superconducting qubit platforms are one of the leading platforms in quantum computation. So of course, people in superconducting qubits have been thinking about reset protocols. And the two main reset protocols are active reset, in which one measures the qubit and then performs an operation to reset it, and unconditional reset, in which you don't know what the initial state of the qubit is, but you, through a pulse sequence, prepare some state that rapidly decays into a ground state and leaving the qubit depleted. So I'm going to be focusing on autonomous reset protocols that contrast with these two time control protocols that I just described. And these two, I mean, one could think like, okay, what's the deal with an autonomous reset protocol, right? Like qubits are gonna naturally relax to the ground state, passively thermalize. We wouldn't need to worry about this. Well, there are two objections. One, the final temperature at which qubits thermalize is usually very high and not useful for computations. And two, the timescales over which qubits thermalize are slow. in terms of scalability, if you have a computing device with lots of units that each of them takes hundreds of microseconds to thermalize on their own, and you want to continue computing, you want to actually do successive computations, but you have to wait a long time between computations so that the qubits erase themselves, that's not going to be very efficient. That's not going to be very scalable. So the alternative that we propose as an autonomous reset protocol is the protocol of quantum absorption refrigeration. So the setup of our system, we have 3 qubits. These 3 qubits have frequencies omega-1, omega-2, and omega-3. And the middle qubit is actually a qubit, and the gap between the first excited state and the second excited state differs from the gap between the ground state and the first excited state, but this quantity, this harmonicity, alpha 2. These 3 qubits are linearly coupled with nearest neighbor couplings, and their energy gaps fulfill this resonance condition in which the energy between, like the energy of the leftmost qubit and the rightmost qubit matches the energy of the middle qubit's largest gap. The leftmost qubit is going to be connected to a waveguide that acts as a thermal bath, and this waveguide is populated by thermal photons with an average number nh, and this qubit is going to decay into the waveguide at a rate gamma 1. And likewise, the middle qubit is going to be connected to a waveguide that also serves as a heat bath with thermal photons at an average number nc at a decay rate of gamma 2. Now, in case the colors and the subscripts didn't tell you, I'm going to be referring to this leftmost qubit as a hot qubit and the middle qubit as a cold qubit. And the rightmost qubit is going to be the target. So this is going to be the system that we're going to be focusing on. This is the system that we want to deplete. This is our target, our goal, to deplete the rightmost qubit in this setup. Now, these average thermal photons are Bose distributed. And these are the experimental parameters for the realization of the device. So the omegas are typical values for frequencies in transmit qubits. And gamma 1 and gamma 2, I want to emphasize this. This is going to be, I'm going to explain why this is important a little bit later. But gamma 2 and gamma 1 are also typical decay rates. But please notice that gamma 2 is 2 orders of magnitude larger than gamma 1. That's going to be important for the reset protocol. And this whole device evolves unitarily under this microscopic Hamiltonian that has the free part of each qubit, plus the interaction terms describing the nearest neighbor couplings. So just a little bit of notation. When I talk about state ijk, it just means the state in which the hot qubit is in the ith state, the cold qubit is in the jth state, and the target is in the kth state. And this resonance condition imposed between the 3 systems is going to single out 2 particularly relevant energy levels. One is 101, in which the hot and target qubits are excited, and the other one is 0 to 0, in which hot and targets are in their ground states, and the middle qubit it's in its most excited state. Now, these 2 states are degenerate, so they're going to be coherently coupled, and they're going to, without any influence, just considering the 3 qubits, they're going to rabbit flop between these 2 states, 101 and 0 to 0. They're going to do so with this effective coupling strength of a few megahertz. And the microscopic Hamiltonian that I wrote in the previous slide can be, like the dynamics can be also read by this effective Hamiltonian in which this coherent exchange between 101 and 0 to 0 is the relevant protagonist in this evolution. Now, the initial conditions, we assume that this hot and cold qubits thermalize with the respective waveguides, and so begin in these mixed Gibbs states. And we assume a worst case scenario for the target qubit in which it begins completely excited, and it's gonna, the task is to take this completely dirty, completely excited qubit and deplete it as well as we can. So the refrigeration process is basically driven by these 3 body interactions in which the hot and target excitations are exchanged with this double excitation in the cold qubit. And this is gonna reset the target qubit by the two conjunct processes. Excitations are gonna hop between, well, like the state's gonna hop between 1 and 1 and 0 to 0, but the cold qubit, it's gonna dissipate into its waveguide at a fast pace. And this is why I emphasized on the mismatch between the two decay rates between the qubits and their waveguides. So the presence of the heat bath is going to bias our system to have excitations in the cold qubit, and bias excitations out of the cold qubit. They're coherently coupled, so excitation, like the state is going to hop into 0 to 0, but once it hops into 0 to 0, instead of hopping back, it's going to rapidly decay. Like excitations are going to rapidly be dumped into the cold waveguide, and as such, they're not going to flow back to 101, and we're going to eventually deplete the excitations in the target qubit. I know that we have space for questions later, but this is basically like the punchline of the refrigeration protocol. So if anyone has like any questions before the results, I can take, like now's a good time. Or else I can continue.
Maybe a quick question.
Yes.
So per each qubit that one wants to work with, one also needs two ancillary qubits in the end. Like, what's the idea for to scale these up in terms of a computer?
Yeah.
Maybe this
So
is a stupid question. I don't know. Yeah.
no. Yeah. Yes. To deplete one target qubit, you would need to have other auxiliary systems at two different temperatures. This temperature gradient is gonna be the one that drives your refrigeration process. So yes, you're right.
Okay, thanks.
Okay. So this is basically how the fridge works. Now we're gonna see how it actually works in real life. So this results slide is probably a little bit information packed, so I'll try to go over it slowly. So in this plot that you're seeing, we have in the x-axis the duration of the protocol, and in the y-axis we have the reset protocol success metric, which is the excited state population of the target qubit. These solid black lines are the theoretical curves for the decay of this population, and the different shaped dots, well, different shaped figures, are the experimental data points. Now, all of these are smooth data curves. It just looks like there's a jank over there because of the change in timescales in the x-axis, but these are all smooth decay curves. Now, these different figures correspond to different average thermal photon number in the hot waveguide. And remember, these are both distributed, so an increasing NH basically means a larger temperature in this hot waveguide. And this green dashed line in the middle is going to be the target's residual excited state population. This basically means this would be the final population that the target would reach if left to thermalize to its own devices. And this blue dotted line is the target's excited state population if it were in contact with the coldest bath available in the system. So why are we bothering with this whole setting a three-body interaction, setting a mismatch between waveguides and qubits and everything? Notice that even for low temperatures of the hot bath, both the theoretical and experimental curves go below this blue dotted line. So that basically means that the refrigeration scheme outperforms passive thermalization. Like this exchange that drives our quantum refrigerator is better than just letting it relax on its own. And it's also not better only in reset fidelity, but also in relaxation time. Yes. So in terms of the operation, we define this steady state population as the population of the target qubits excited state after a long time, which we take to be 100 microseconds. And we now look at how this quantity, like this long time population, varies as we meddle with the temperatures in the heat baths. So in this first plot, the cold bath temperature is going to be fixed while the hot bath temperature is changed. So notice that this steady state population decreases as the temperature in the hot bath goes higher and higher. On the other hand, if you fix the hot bath temperature and meddle with the cold bath temperature, this increase in the cold bath temperature actually hinders the reset protocol. So bath temperatures serve as knobs for the cooling protocol, and we can think of this in an intuitive way by recalling what I mentioned early in the presentation, where this refrigeration process is going to be driven precisely by the thermal gradient between the available heat baths. So if you have a large thermal gradient, you have a lot of free energy to perform your task, while if this thermal gradient is slow and the temperature is comparable to each other, then really the reset task doesn't have as much free energy to actually perform the action of removing excitations from the target qubit. As figures of merit, this minimum steady state population takes values, like the minimum steady state population takes values of 3 times 10 to the minus 4, which translates to an effective temperature of the qubit of 22 millikelvin, which is lower compared to previous state-of-the-art protocols. And it's close to the theoretical prediction of 19 millikelvin. And also the reset time, which is how long it takes for the population to go below 1%. The lowest reset time in the experimental data was of 970 nanoseconds. So what does all of this mean? Well, first of all, this is a proof of principle demonstration of a useful autonomous quantum machine that has a usable protocol in superconducting quantum computers. Now, I'm saying proof of principle because in this particular instance, the heat baths were realized by waveguides, but heat baths in superconducting qubit platforms are available due to the fact that these are usually embedded in dilution fridges that have different layers at different temperatures. So connecting different qubits at different layers of the dilution fridge naturally gives you different temperatures, which is, again, what drives this protocol. And besides being just like a curiosity or just like a quirky device, it's a curious, quirky device that also is performance competitive. The reset fidelity, as I mentioned, is lower than other non-autonomous protocols, like this final temperature of 22 millikelvin compared to the 40s millikelvin temperatures in these previously leading protocols in the literature. And introducing the presence of autonomy worsens the reset time of the protocol compared to these state-of-the-art protocols. Now, what lies next? Well, first of all, Simone Gasparinetti, the leading experimental PI in this paper, mentioned that these experiments were basically building and I quote, these are his words, building an autonomous quantum refrigerator out of the Lego pieces that we have lying around in our lab. So these, like, the device is not tailored precisely to this task. So by doing that, one could expect a better performance of such a device, that is actually tailored for this. And also in terms of thinking about autonomous quantum machines that are useful beyond this protocol, we talked a little bit about general criteria in this paper here. Like, we thought about sort of like more abstractly, not just like a fridge, but also like other autonomous protocols, what are like the minimal conditions that these should fulfill, sort of in the spirit of the De Vincenzo criteria for quantum computers. And recently we posted on the archive this paper detailing some experimental proposals for gate protocols in different leading platforms in the quantum computing game. So it's, besides the superconducting qubits, we're also proposing gate protocols for trapped ions and Rydberg atoms that work without time-dependent external control. So I want to thank you for your attention, and I'll take any questions that you may have.
So thank you. If there is any question, please go ahead. Perhaps I can start again. In your little example where we have three systems, we have a target qubit and then we have the hot and cold bath. If I want to have more qubits to erase in parallel, will the same analogy work if I have like 3, 4, 5 more qubits to erase altogether? Will it scale this example that you show, or something different will happen?
In terms of scalability, yes. I mean, this as I mentioned, like near the end of the talk, this is thought in a superconducting qubit platform. So like the fact that you just connect different qubits in different layers of the dilution fridge. So in terms of scalability, you have the heat baths, you have other parts of the circuit lying around. So you could easily just swap some of the connections and perform this reset protocol in more target subsystems. I don't know if that answers your question. I don't know.
Yeah. I have.
Thanks.
Is there any other question?
Yes, so I've got maybe a similar question related to the scalability aspect. And yeah, I'm not entirely sure whether the question fits more to Nicole or to Jose. But yeah, you've demonstrated a really nice proof of principle kind of experiment for showcasing how quantum thermodynamics can be useful. Now, I was just wondering how this fits back to the original kind of machines that the 18th century people had in mind in thermodynamics, because they were thinking surely not of Landau erasure, Sillot's engines, qubit resets, but bigger systems. And yeah, Nicole's talk, she was talking about that thermodynamics is about formulating the laws of thermodynamics for small quantum systems far from equilibrium and so on. I was wondering, yeah, again, related to this small aspect or scalability aspect, to what extent maybe you see this framework helpful maybe to realize, can we go back to the original kind of domain of at least collective scalable systems where we can see quantum effects that could be useful in thermodynamic tasks, so more large scale, or are we constrained to those kind of small qubit systems? Because we see similar developments in quantum physics, like a couple of decades ago with states of matter where we had collective quantum states. So I was wondering whether there's also a role to play for thermodynamics, or whether it's concentrated on those kind of small systems. Hope that makes sense.
Yeah. I think that the autonomous quantum machines literature that I've encountered with, I'm not saying this is like the only autonomous quantum machines literature that there's out there, usually focuses on like the bare minimum, like the smallest possible refrigerator kind of thing, the smallest possible heat engine. So these always deal with like units that you want to, units in terms of a single qubit or a single system that you want to perform a task on. I'm not exactly sure, and I mean Nicole can of course barge in if she has an example, but I cannot think of any like autonomous quantum machine that that involves like a collective system being performed a task on. But out of the top of my mind, I cannot think of any because of like the intrinsic.
I can add to that response. In general, in quantum thermodynamics, people do tend to start out with single qubit examples because a lot of us were trained in quantum information theory and we like to think about qubits. But as
quantum thermodynamics has grown over the past 15 years, there's been a lot of merging of quantum thermodynamics with neighboring fields such as many-body physics, atomic molecular and optical physics, and condensed matter physics. And some of that growth has been in for example, the proposal of quantum thermal machines that rely on many-body quantum properties, such as certain regimes of quantum matter. The one that I've worked on is a quantum engine that implements a quantum Otto cycle and relies on the transition between the many-body localized regime of matter and a regime of matter that obeys the eigenstate thermalization hypothesis. Both the eigenstate thermalization hypothesis and many-body localization, many-body effect. And this is just one example of how people have been incorporating things like phase transitions and large-scale entanglement into quantum thermal machines. So that is a way in which people have been considering scaling up quantum thermal machines.
Okay. Thank you.
Okay, I think I have just a quick question in general, and I don't know who wants to answer. At a certain point, I heard about quantum batteries, and I would like to know if there is a easy intuition to what are those.
Yeah, I can explain there because I wrote a section of my book specifically about quantum batteries, so I had to go through this process with myself so that I could understand what they were all about. So suppose that we consider a quantum battery as a qubit, quantum two-level system. One of its energy levels corresponds to a lower energy, the other level corresponds to a higher energy. And a classical version of this is just a bit with two energy levels. We can't perform anything like a Hadamard operation. We can't measure anything like sigma x. We can't entangle the batteries. Suppose that our goal is to start off with batteries in their ground states and end up with batteries in their upper levels. We ask how quickly, or what is the greatest power with which we can charge the batteries, maybe on average over the batteries. It turns out that we can charge the batteries with a greater power if we entangle them than if we don't entangle them. There is a relatively simple intuition about why this result shouldn't seem unreasonable. Suppose that we're talking about charging just one battery. We can visualize its state as points on the Bloch sphere or in the Bloch sphere. And the state begins with this Bloch vector. It ends up with this Bloch vector. We could charge the battery along this path. We could charge the battery along that path. We could do a spiral shape. There are so many different paths we can take through the state space. Then suppose we shift to thinking again about multiple quantum batteries. Their collective state is in some state space, and we need to start the state off at one point and end it at another point. Again, we can think about multiple paths for the state space, although it's not so easy to visualize this state space. Suppose that we don't allow ourselves to entangle the batteries during the charging process. We are restricting ourselves to only a few paths. Then suppose that we allow ourselves to entangle the batteries during the charging process. We are now opening up our options to all the possible paths in the state space. And it makes sense that one of the extra entangling paths might very well lead to a greater power than one of the more restricted paths.
Perfect. It was a perfect image. So thank you very much. So if there is no other question, I think we can thank the speakers again. And
thanks very much for having us.
Thank you. And I hope to see you on the next qmeet next month. And see ya.
Yeah. Thanks for the invitation. Bye.
Thank you.
Thanks.
Bye-bye.
Bye.
Guys, I will close the meeting now, okay?
Mhm.
Bye-bye. Thanks for
Bye. Bye.